At the heart of our understanding of the universe lies one of the most compelling ideas in modern science, the Big Bang theory. This theory suggests that the universe began as an extremely small, infinitely dense point, a singularity which underwent a massive expansion around 13.8 billion years ago. From this initial burst of energy and matter, the universe rapidly expanded and cooled, allowing atoms, molecules, stars, galaxies, and eventually planetary systems to form. This model has not only explained the large-scale structure of the cosmos, but has also been supported by various empirical observations, including the cosmic microwave background radiation and the abundance of light elements such as hydrogen and helium. For decades, the Big Bang has stood as the dominant explanation among physicists, offering a coherent narrative about the universe's beginning and its evolution. However, as technology has advanced and new instruments like the James Webb Space Telescope have come online, fresh data has emerged, data that doesn't entirely fit within the traditional Big Bang framework. These observations suggest that our universe may be older or more complex than previously believed, and that the Big Bang may not have been the absolute beginning, but rather a significant moment in a much larger story. Recent theoretical developments are pushing the boundaries of cosmological thinking even further. Some physicists propose that the universe may not have originated from a singular starting point at all. Instead, it could be part of a vast, eternal cycle of expansion and contraction, a concept known as cyclic or oscillatory cosmology. In this view, the universe repeatedly goes through phases. It expands, grows cold and diffuse, then contracts and collapses into a highly dense state, only to begin the process anew. This continuous cosmic loop may have been repeating indefinitely into the past, and could continue endlessly into the future. One of the leading voices challenging the conventional interpretation of the Big Bang is Professor Brian Cox, a renowned physicist and science communicator. He has questioned the very foundation of the theory by addressing a critical philosophical issue: how can something come from nothing? According to Cox, the idea that the universe simply emerged from a state of complete non-existence is both counterintuitive and scientifically troubling. His perspective underscores a deeper tension between our current physical models and the fundamental metaphysical questions they attempt to address. Adding further weight to this paradigm shift, the James Webb Space Telescope has observed galaxies that appear to be far more mature than what should exist if the universe had a clean beginning 13.8 billion years ago. These findings suggest that either our understanding of galaxy formation is incomplete, or that the timeline of the universe itself may need revision. If the Big Bang is not the true point of origin, then what came before it? This profound question invites us to explore the outer edges of physics and cosmology in search of more comprehensive theories. While the Big Bang theory remains robust and well supported in many respects, it does have limitations. Specifically, it does not account for the actual mechanism or cause of the singularity from which it begins. Our current physical laws, particularly general relativity and quantum mechanics, struggle to describe the conditions that existed at the very start. As we approach the singularity, the equations of general relativity break down, and concepts such as time and space cease to have conventional meaning. This breakdown signals a need for a new, more unified theory that can accurately describe such extreme conditions. Enter string theory, a candidate for the long-sought theory of everything. String theory attempts to unify the four fundamental forces of nature, including gravity, within a single theoretical framework. Rather than point-like particles, it posits that the fundamental building blocks of the universe are tiny, vibrating strings. These strings operate at energy levels and scales far beyond what current experiments can reach, but they offer intriguing new ways to think about the universe's birth. One such idea is the ekpyrotic model, derived from the Greek word for conflagration or fire. This model suggests that the Big Bang may not have been a singular event, but the result of a collision or interaction between higher dimensional spaces or branes. From the ekpyrotic model springs the idea of cyclic cosmology, a theory with ancient roots but now backed by modern mathematics and physics. Cyclic cosmology posits that the universe undergoes eternal cycles of death and rebirth. Each Big Bang is not a beginning, but a transition from a previous cosmic phase. In each cycle, the universe expands, evolves, and then contracts or fades into a low-energy state, setting the stage for the next cycle. A leading proponent of this modern cyclic model is Sir Roger Penrose, a Nobel Prize-winning physicist known for his work on general relativity and black hole singularities. Penrose has introduced a concept known as conformal cyclic cosmology, CCC, which proposes a deep mathematical connection between the distant future of our current universe and its distant past. According to Penrose, as the universe continues to expand and cool, it will eventually become a sparse, cold void dominated by black holes. Over unimaginably long timescales, even these black holes will evaporate via Hawking radiation, leaving behind a universe of almost nothing, except, perhaps, for a scattering of photons. Here is where Penrose's insight becomes remarkable. Using a mathematical technique called conformal transformation, he shows that this final, cold, and empty state of the universe can be mathematically mapped onto the hot, dense conditions of a new Big Bang. Conformal transformation is a geometric operation that alters the size of objects while preserving their shape. In this context, it suggests that the end of one universe and the beginning of the next are not just metaphorically connected, they are, in a very real mathematical sense, the same. Under the extreme conditions at both ends of time, the concepts of distance, size, and even time itself lose their usual meanings, making such a transformation conceivable. This leads to a striking vision, a universe that is born out of the near-nothingness, left behind by its predecessor. From a physical perspective, the end state, empty and devoid of matter, becomes the fertile ground for the birth of a new universe. The cyclical nature of this process elegantly bypasses the need for a first cause, since each universe is birthed from the remains of the one before it. In Penrose's model, each cycle, or aeon as he calls it, may be slightly different from the previous one due to quantum variations. Quantum mechanics tells us that systems exist in multiple possible states until measured or interacted with, at which point they collapse into a single outcome. Penrose theorizes that these quantum fluctuations in each aeon could result in minute variations in the next, and that these might leave detectable imprints in the cosmic microwave background radiation, the afterglow of the Big Bang. In fact, Penrose and collaborators have claimed to identify subtle circular patterns in this radiation that could be evidence of pre-Big Bang activity. This notion opens new doors for experimental physics. If evidence from cosmic background radiation supports the cyclic model, it could revolutionize our understanding of cosmology. It would not only reshape our ideas of time and space, but also offer a scientific framework that addresses the deep, philosophical question: why is there something rather than nothing? As we explore these ideas, we are reminded that cosmology exists at the intersection of physics and philosophy. Even if we accept the cyclic model, profound questions remain. What mechanism initiated the first cycle, if there was one? Could there have been an infinite series of cycles, stretching eternally into the past? Or is there a single cycle that replays endlessly, self-sustained by the laws of quantum gravity? Three possibilities emerge within the scope of physics. First, there might be no underlying cause or explanation for the cycles. They simply exist. Second, the universe may be an infinite sequence of distinct cycles, each emerging from the quantum residue of the one before. Third, we could be living in a universe that reboots itself repeatedly, with its ending phase providing the seeds for its own rebirth, perhaps in a grand cosmic loop, where past and future are inseparably intertwined. Ultimately, these possibilities offer an elegant resolution to the problem of uncaused origins and help frame our understanding within a broader, physically plausible context. Yet the deeper metaphysical questions about why these cycles exist at all and what lies beyond them remain unresolved. What do you think? Does the idea of a cyclic universe challenge or enhance your understanding of existence and cosmic origins?